In this video, we'll take a look at how to use partial fractions to integrate rational functions whose denominators consist of non-repeated linear terms. More specifically, we're going to be looking at rational functions whose denominator can be factored into the form x minus a1 times x minus a2 up to x minus an, where each of these factors are distinct. So in other words, all of the a's are distinct numbers from each other. We know that in this particular case, the partial fraction decomposition for a rational function will have the following form. We'll have a constant a1 over the factor x minus a1, plus another constant a2 over x minus a2, all the way up to a constant a sub n all over x minus a sub n. We now look at how to use this partial fraction decomposition to rewrite our integrand and evaluate our integral. In this example, we want to evaluate the integral of x squared plus 2x minus 1 all over x cubed minus x squared minus 2x dx. This is an integral of a rational function, and so partial fraction decomposition is a natural approach to evaluate this integral. The first thing that we do here is we look at the degrees of the numerator and denominator, and we notice that the numerator here is a quadratic, so it has degree 2, whereas the denominator is a degree 3 polynomial because of the x cubed term at the beginning. And in this case, the degree of the numerator is smaller than the degree of the denominator, and so this is perfectly set up to use partial fraction decomposition. We always need the degree of the numerator to be strictly smaller than the denominator in order to write down our partial fraction decomposition and evaluate the integral using it. Once we have verified that, the next step is to factor the denominator completely. And so here our denominator is x cubed minus x squared minus 2x. We notice that each of the terms has a factor of x, so we can first factor out an x from every term. And when we do that, the remaining expression is x squared minus x minus 2. And that is a very straightforward factoring quadratic. It's going to factor as x minus 1 times x plus 2. And so here is our completely factored denominator, and we notice that we have 3 linear terms. We have x, x minus 1, and x plus 2, and none of them are repeated. So we have non-repeating linear factors here in the denominator. We can now write down our partial fraction decomposition for this particular rational function. So we know we're going to start with our original rational function, x squared plus 2x minus 1, and I'm going to rewrite the denominator in the factored form that we just determined. So the denominator here will be x times x minus 1 times x plus 2. That, of course, is the same thing as x cubed minus x squared minus 2x. Because we have non-repeated linear terms, we're going to be able to write this partial fraction decomposition as a sum of 3 terms, one for each linear factor. So we will have some constant a over our first linear factor of x. We will have some other constant b over the second linear factor, x minus 1. And add to that a third constant c over the third linear factor, x plus 2. Now, in our previous formula for this partial fraction decomposition, our constants were labeled as a1, a2, a3, etc. Here we're using a, b, and c. Typically, using a, b, c, then d and e if necessary makes it a little bit easier algebraically since we have distinct letters representing the distinct numbers, but we can certainly use subscripts here if we'd like. Now, once we have our partial fraction decomposition, the first step to evaluate the integral is to find the exact values of a, b, and c. And in order to do that, we're always going to take this equation and multiply by the original denominator. In this case, that would be x times x minus 1 times x plus 2. And when we do this, a lot of things will cancel, and will cancel very cleanly. So on the left-hand side, we're going to multiply by our denominator, and that will cancel entirely. And so we're just left with our numerator, x squared plus 2x minus 1. On the right-hand side, we're going to multiply each of the three terms separately by x, x minus 1, and x plus 2. And when we do, one of the factors is going to cancel with the denominator in that term, and the other two will remain being multiplied by the constant. So for example, when I multiply a over x by this product, we have an x in the denominator and an x that we're going to multiply by, so these two x's here will cancel. But the other two factors, x minus 1 and x plus 2, will remain, and we'll end up just multiplying a by those two factors. And so here we're going to be left with a times x minus 1 times x plus 2. Again, the x does not appear there because it cancels with the x in the denominator of a over x. When we multiply the b term by this quantity, the x minus 1s will cancel, and that will leave b being multiplied by x and x plus 2. And for our last term, the x plus 2s will cancel, which will leave c being multiplied by x and x minus 1. And so we've rewritten our partial fraction decomposition as the equation x squared plus 2x minus 1 equals a times x minus 1 times x plus 2 plus bx, x plus 2, plus cx, x minus 1. And now we use some strategic choices of x to solve for a, b, and c, and ultimately to evaluate our integral. In order to solve for a, b, and c at this point, we're going to substitute certain values of x into the equation so that certain terms on the right-hand side will vanish, leaving only one of our constants at a time. For example, we might notice that if we let x equal 0, the b and c terms will both disappear because b and c are both being multiplied by x along with some other factor. But if x were 0, we'd be effectively multiplying b and c by 0. And so here our first choice of x will be x equal to 0. When we substitute x equal to 0 on both sides, we get a negative 1 on the left-hand side because x squared plus 2x will become 0. So we have 0 plus 0 minus 1. And on the right-hand side, we have a times 0 minus 1, which is negative 1, times 0 plus 2, which is 2. And as previously mentioned, the b and c terms will both become 0. And so we have negative 1 equals essentially negative 2a here. And so from that, we can see that a is going to equal 1/2. Negative 1 over negative 2, which is positive 1/2. And so we know that a is going to equal 1/2 in our partial fraction decomposition. We can use similar logic by choosing x to be 1. This will get the a term with the x minus 1 factor and the c term with the x minus 1 factor. Those will then vanish and we'll be left with just the b term. So substituting 1 into the left-hand side, we're going to get 1 plus 2 minus 1, which will end up being just 2. The only term on the right-hand side that remains will be the b term. So we'll have b times 1 plus 2, which is 3. So we have 3b there. And so to solve for b, we divide both sides by 3, and we see that b is going to equal 2/3. So b will be 2/3 in our partial fraction decomposition. And last but not least, we're going to let x equal negative 2. And this will account for the x plus 2 in the a and b term. Those will then vanish, and we'll be left with our c term only. So on the left-hand side, we substitute negative 2 in for x, and we get 4 minus 1, and all that becomes negative 1. The a and b terms disappear, and we're left with c times negative 2 times negative 2 minus 1, which is negative 3. And so this is 6c when we multiply that out. And so it looks like c is going to end up being negative 1/6. And so our partial fraction decomposition will be the expression that we had previously with a, b, and c being 1/2, 2/3, and negative 1/6, respectively. So using this partial fraction decomposition, we can take our original integral, x squared plus 2x minus 1 over x cubed minus x squared minus 2x dx, and rewrite it as an integral of our partial fraction decomposition, which consists of a over x, or 1/2 over x, plus b over x minus 1, or 2/3 over x minus 1, plus c over x plus 2, or negative 1/6 x plus 2. Each of these three terms can be easily antidifferentiated using the natural log function, and so we end up with an integral of the form 1/2 natural log of the absolute value of x plus 2/3 natural log of the absolute value of x minus 1 minus 1/6 the natural log of the absolute value of x plus 2 plus c. Note that the absolute values are important here in all three cases because depending on the value of x, the expressions x, x minus 1, and x plus 2 could certainly be 0 or negative, and when we use the natural log function, we can only evaluate positive values with that. And so we need to ensure those expressions are positive before we take the natural log. If you'd like to try a similar example, you can pause the video and evaluate the integral of x plus 1 over x squared plus x minus 6 dx. Resume the video to see the full solution. We quickly note that the degree of the numerator is 1 and the degree of the denominator is 2, and so our numerator has smaller degree. We then factor our denominator as x plus 3, x minus 2, which consists of two non-repeated linear factors. So x plus 1 over x plus 3 times x minus 2 will have a partial fraction decomposition of the form a over x plus 3 plus b over x minus 2. We can multiply through by the product x plus 3, x minus 2 to obtain x plus 1 equals a times x minus 2 plus b times x plus 3. We can substitute in x equal 2 and x equal negative 3 here to get the terms to cancel on the right-hand side, and doing so, as shown here, will yield b equals 3/5 and a equals 2/5. Once we substitute a and b into our partial fraction decomposition, our original integral will be equal to the integral of 2/5 over x plus 3 plus 3/5 over x minus 2 dx, which will antidifferentiate to 2/5 natural log of the absolute value of x plus 3 plus 3/5 natural log of absolute value of x minus 2 plus c. In this example, we want to evaluate the integral of 2x cubed minus 4x squared minus x minus 3 all over x squared minus 2x minus 3 dx. When we look at this rational function inside the integral, we notice that the numerator has a degree of 3 because of the x cubed term, and the denominator has only degree 2. And so here we have a rational function where the numerator has larger degree. And when we have that, the first step of our partial fraction decomposition process is to perform polynomial long division to find a polynomial where the degree of the numerator is smaller than the degree of the denominator. So let's quickly recall how polynomial long division will work. So here our divisor polynomial is x squared minus 2x minus 3. And we're going to divide that into our dividend of 2x cubed minus 4x squared minus x minus 3. And our steps here are going to mimic that of standard long division that you learned in elementary school. We're going to look first at our leading terms. We have x squared and we have 2x cubed. And we ask ourselves, what do we need to multiply x squared by to get 2x cubed? Or alternatively, what do we get if we divide 2x cubed by x squared? And the answer to either of those questions is just 2x. And so now we take our partial quotient here of 2x, and we're going to multiply 2x by everything here in our divisor. And so in this case, we get 2x times x squared, which will be 2x cubed. 2x times negative 2x will be minus 4x squared. And 2x times negative 3 will be minus 6x. And now we subtract these two expressions. And so 2x cubed minus 2x cubed gives us 0. Negative 4x squared minus negative 4x squared, again, gives us 0. Negative x minus negative 6x gives us a positive 5x because we're subtracting a negative. And we have negative 3 minus 0, which is just negative 3. And so now I have this polynomial of 5x minus 3 remaining. And this is a degree 1 polynomial, just has 5x as the leading term. And that's smaller than our divisor's leading term of x squared. So the degree here is smaller than our divisor. And so this is where the process stops. So this particular process only goes one step. However, if this degree of 5x minus 3, if that term had a larger degree than 2, then we would just repeat this process one more time. And so what this long division algorithm has shown us is that our original function, 2x cubed minus 4x squared minus x minus 3 over x squared minus 2x minus 3, this can be written as the quotient 2x plus our remainder 5x minus 3 over our divisor, x squared minus 2x minus 3. And this term here has the standard partial fraction format where we have a degree 1 polynomial over a degree 2 polynomial. So the degree in the numerator is smaller. And so we can use partial fractions on this particular rational function. So we can find a partial fraction decomposition of this expression. We do have to remember when we integrate to also include the 2x as well. We're going to integrate that term there, but that does not require partial fractions. And so at this point, if you'd like to pause the video, try to use partial fractions to expand and evaluate the integral of 5x minus 3 over x squared minus 2x minus 3. And then remember to add in the 2x term at the beginning as well. You can resume the video in a few seconds to see the full solution. The denominator factors as x minus 3 times x plus 1. So our partial fraction decomposition will have the form a over x minus 3 plus b over x plus 1. We can multiply through by the denominator to get 5x minus 3 equals a times x plus 1 plus b times x minus 3. Letting x equal to 3 in that equation will tell us that a is equal to 3. And letting x equal negative 1 in that equation will tell us that b is equal to 2. We can substitute those two quantities back into our partial fraction decomposition. And we do need to remember that we have this 2x term as well from the quotient from the long division that we had earlier. And so our integral consists of the integral of 2x plus 3 over x minus 3 plus 2 over x plus 1 dx. And integrating each of those three terms, we have x squared plus 3 natural log of the absolute value of x minus 3 plus 2 times the natural log of the absolute value of x plus 1, all plus our arbitrary constant c.